Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel TanmoyChem. Today's topic of discussion is a very interesting MCQ. I request everyone, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as explanation. I believe we have tried. Let's start. Now the question, the correct order of energy generation with respect to one CO2 emission of these compounds. Okay, what is the correct order? Or this question could be asked in a different way, that the correct order of stability of the following hydrocarbon compounds. Now, when this question asks to you, it becomes very confusing. So, stability, how can I judge? Because it says C3 hydrocarbon, it says C4, and it says C5. How can I judge? You can judge it with respect to heat of combustion data for per molecule CO2 emission. So, that's why this point is given. So, apparently, this two question looks different, but actually they are asking the same thing. So let's go into the details. So what is the basic concept regarding such kind of reaction? So if you look at, there's a chemical reaction having reactant to product. So this is your reactant energy, this is your product energy level, and obviously I am considering this is a one-step reaction. That's why this is my transition state, this one. Okay, now what happened if you look at the reactant's energy is slightly higher compared to the product, means this is energy action, this is reaction coordinate. So obviously in this case my delta G will be final minus initial. Final means product, lower energy, so low, reactant high, so low minus high, it will be negative. So delta G is negative. So okay, you can say, sir, this is exothermic reaction. Yes, it is exothermic. So it produces it like the combustion of hydrocarbon. Okay, so this is actually the overall reaction. Now in this case, the hydrocarbon, there are three kinds of hydrocarbon we have taken as a model substance, I mean reactant. What are the product? Products are actually CO2 plus water. By the way, it's not only hydrocarbon plus oxygen. So it produces CO2 and water. Obviously the number will vary case to case basis. Now if you want to judge it, how could you compare them more accurately? If you look at the complete combustion in terms of excess oxygen I'm talking, and by the way, if you look at heat of combustion, what does it mean? Amount of energy released or consumed upon combustion of 1 mole of a compound or 1 mole of a hydrocarbon in terms of excess oxygen, such that complete combustion should take place and ultimately it will result into CO2 and water. By the way, if I say this propane, it's a C3 hydrocarbon, so it releases 3 CO2, 3 water. By the way, why these reactions are exothermic? Because the product, carbon dioxide and water, they are more stable compared to the reactants like alkane, cycloalkane and oxygen. So here it's a 4, 4, 5, 5. Now whatever energy release for every reaction, if you divide this energy amount by, for first case 3, second case 4 and third case 5, then it will be a proper understanding about the energy release for each CO2 unit. And you can look at the data here. So if you look at cyclopropane, N is equal to 3, then the heat of combustion, obviously here they have given kilocalorie unit, 468. But what is the delta H for per CO2 unit? This is important, it is 56. For cyclobutane, value is more because more number of CO2 and water is produced, but value is 153. For cyclopentane, 148. So what this message says, now if you go back to the example, if your reactant energy higher and product, by the way, product energy is similar, so if your reactant energy higher, this delta H value will be more negative, means more exothermic. So what can I conclude from here? Cyclopropane is less stable. So that's why the energy release for per CH2 unit, by the way, do not compare here, you'll be confused. Per CH2 unit, it's more. Cyclobutane, cyclopentane, and if you go to cyclohexane, it is this. Okay, now along with this, there is another data called ring strain. If you look at cyclopropane's ring strain is very high, that's 27.6. Cyclobutane 26.4. Cyclopentane 6.5. So ring strain is reducing, and at cyclohexane it's 0. So that's not the question of today's discussion. So if you look at the ring strain is getting reduced from cyclopropane to cyclobutane to cyclopentane, and that's why ring strain more means less stable. If less stable, so per CH2 unit wise, if you think, it will release more energy. Okay, so this is a very interesting. And if you say, sir, beyond cyclohexane, if I go heptane, this ring strain also increases, that's why this value again increase. I'll not go in details in those values. So what was our question? The correct order of energy generation with respect to one CO2 emission. Now lesser the hydrocarbon or alkane stability, in this case because of ring strain, higher will be the energy release. So here ring strain is maximum, so the energy release will be maximum for 1 second for this and minimum for this 5 member. Why? Because ring strain is minimum among 3. So what is the order? The correct order of energy generation: 1 will generate maximum energy, so 1 greater than 2 greater than 3. So option A is the right answer. By the way, if you get this question, how could you solve it less than 30 seconds in your exam hall? First you need to understand 1 molecule CO2 emission. So you cannot say, okay, the number factor here C3, C4, C5 have eliminated. So for 1 molecule perspective, you need to think with respect to the energy profile diagram I have shown. So which one is less stable, that will produce more energy, because my product is same. Here reactant is different. If reactant is more stable, reaction is more exothermic, more amount of energy is released. So, and this is least stable because of ring strain. So from that perspective, you can get this answer very quickly. Okay, so this is the overall discussion, and in conclusion, what you have learned today, that energy release of a fuel is dependent on the number of carbon and hydrogen present in the molecule, but the stability of hydrocarbon could be concluded easily by release of energy with respect to each CO2 emission. So very important. In this way, you can check also the fuel efficiency for per CO2 emission. I mean, since global warming, climate change is a hot topic nowadays, if you think from this perspective, it's better. Now, lesser the stability of parent hydrocarbon, higher will be the energy release, as well as during the combustion or chemical reaction, anything. And less stable hydrocarbons are better fuel, as it releases more energy upon complete combustion. Okay, so this is the overall discussion. Thanks for watching. See you in my next video. Bye bye.